With that, it's time now for the next session of the day, and we have with us Professor Partha Talukdar, who's currently a staff research scientist at Google Research Bangalore, where he leads a group focused on natural language understanding. He's also an associate professor on leave in Department of CDS and CSE at IISC Bangalore. Partha founded Genome, an enterprise knowledge graph company with a mission to help enterprises make sense of unstructured data. His recent research focuses on graph-based learning algorithms for large-scale information extraction and data integration, temporal information processing, automatic knowledge harvesting from large data, and neurosemantics. Partha is a recipient of several awards, including an Outstanding Paper Award at ACL 2019. He's a co-author of a book on graph-based semi-supervised learning. He has presented more than 100 papers in international conferences. Here to speak on scaling natural language processing for the next billion users, Professor Partha Talukdar. Professor, you are muted.
Yes, yeah. Hi.
Hi.
Thanks a lot, Anvit. Yeah, I'll just share my screen.
Just a couple of announcements before I hand it over to you.
Sure.
Please do post your questions in the Q&A box, and Professor, maybe you could keep some 5 minutes towards the end, 5 to 10 minutes towards the end for questions. That way, we'll have some good time for the questions that are coming in.
Absolutely.
Yeah, and any questions which are already there, if the professors from the previous talks are still available, you can answer them in the Q&A box itself. Thank you so much. Over to you, Professor.
Sure. Okay. Thanks a lot to Santosh, Balaji, and the other organizers for having me. And good morning to all of you. And also thanks to Mosam for setting the very appropriate context for this particular talk, where I will be talking about some of our recent work in scaling natural language processing to the next billion users, pushing the boundaries beyond, say, the high resource languages where we typically deal with NLP. And for this particular talk, I will be focusing on Indian language processing. So let's get into it. So Indian languages, as you are probably already very familiar. So we are a very complex and rich country linguistically. So we have 22 scheduled languages and more than 1,500 total languages, lots of different scripts, and more than 1.3 billion speakers. And the topic of code mixing came up. It's very common for many of us to be multilingual and know multiple languages. And not just that, we also mix multiple of these languages in the same sentence, right? Or in the same paragraph. And the number of people who have access to internet is growing over time. And they have a natural need to access information and consume content in local languages. And according to latest statistics from June this year, there are more than 800 million users who have internet access in India. And that's a growing number. But on top of that, only 10.6% of the population have some knowledge of English. And that's according to 2011 census. So as you can see, vast segment of the population don't have, cannot understand English, while a lot of the good quality content gets generated in English and other higher web resource languages. So, so the question is, how can we, do better with Indian language processing so that we can democratize information access for all of these users? And while I'll be talking about the Indian language scenario here in this particular talk, the hope is that the techniques and the approaches that we develop could be applicable more broadly to other languages with similar settings, for example, say African languages or Latin American languages down the line. So now coming back to the Indian languages, so in this particular plot, you see the 22 plus English, the 23 scheduled Indian languages, and the number of speakers in these languages. So Hindi, we have about 450 million or so speakers. But then again, we think of Hindi as a monolithic language but it turns out that there are 40 plus related languages and dialects of Hindi alone, right? So it's a very complex, and lots of nuances are needed. But then also, if you look beyond the top 10 or so languages, there are about more than 127 million speakers, native language speakers in these languages, just even among these 23 scheduled languages. And that turns out that's the 5 times the total population of all of these Scandinavian countries taken together. So as you can, hopefully this reinforces the fact that there are lots of speakers of these languages, and currently we are not doing very well in serving the needs of the speakers. So what's the current state? So this is a snapshot in terms of availability of data that I took from the AI for Bharat webpage. And it shows that just for a handful of important tasks which are listed in these rows for a few Indian languages, the availability of data situation is quite poor, right? So where the crosses mean that no resource for that particular task exists for these languages, right? And so if you don't have labeled resources, that's a problem, not just during training, but I would say more importantly, during even evaluation, because even if you have built a model, which is say able to handle multiple languages, or you don't require say training data for a particular language, but you still need to be able to evaluate that particular model. And so you need at least some amount of labeled data for evaluation, which doesn't exist for pretty much all Indian languages for a large number of tasks. And what you see here is a snapshot, right? So the situation with labeled data is a big bottleneck, and we cannot change that overnight. That requires investment of resources. So in this particular talk, I'll be focused on how we can do more with less, exploiting ideas of multilinguality that Mosam was also talking about. And along the way, at least for evaluation purposes, we have also created new data sets. So I will point you to those as we go along. So my talk is going to be in 3 parts. So on top, you have this block for Indian languages. On the lower left, you have say this block of high web resource languages like English. And then you also have an external knowledge in the form of knowledge graph. So now the question is, the first part will be focused on how we can leverage these high web resource languages to bootstrap models for these low web resource languages like Indian languages, right? So that's part 1. Second one is that all of these Indian languages are not independent of each other, right? They are they belong to certain language families, like say broadly the Indo-European and Dravidian languages. And there are, and they have common roots respectively in their language families. So because of that co-evolution from a common source, they do have lots of overlaps in terms of word forms with some variations, and then a sentence structure. So how we could exploit those relatedness to help improve Indian NLP. And then finally, how I can connect these kind of external resources, like say knowledge graphs, for processing Indian language data. So these will be the 3 parts in my talk. So let's first see about the transfer supervision part, right? So before we get here, so most of it is going to be around multilingual NLP, but just to make sure we are all on the same page, here is one slide introduction to pre-trained language models like BERT, where we basically given a sentence which says that Dimapur is the 2nd most linguistically diverse district in India. By the way, it turns out Bangalore is the first one, and then Sonitpur in Assam is the 3rd one. And in all of these 3 districts, more than 100 languages are spoken, and that's according to 2011 census. So in case of masked language model, what we do is basically we mask certain words in the sentence, maybe around 10 to 15% of the tokens. And then we basically train our language model, which will try to predict this masked token by utilizing the rest of the context from the sentence, right? So this is basically what is called as the masked language model. And in this way, you basically learn embeddings for all of these tokens. And by doing this kind of like pre-trained modeling, learning these embeddings in a contextual way, you are now able to fine-tune this common representation into a variety of different downstream tasks, which is, say, question answering, named entity recognition, dialogue, so on and so forth. And this has revolutionized NLP, and pretty much all of the state-of-the-art methods would follow this kind of like a pre-training step followed by a fine-tuning, task-specific fine-tuning step. Now, this is, and as I mentioned before, so BERT is one example of this. Similarly, XLMR, all of these are different examples of pre-trained model. But what I've talked about here are all monolingual, right? So in this particular case, I'm just dealing with English. So what's remarkable is that these models can also be applied to build multilingual models, pretty much relying on this kind of masked language model objective. So in this case, I give data from a variety of different languages. So say in this particular case, a variety of Indian language data. So I do this kind of masked language model, and some other losses also you can incorporate, but to keep things simple, I'm not going into those today. And we learn some sort of common representation across all of these different language data. And then this is my pre-trained embeddings. And now these pre-trained embeddings and models, I could now fine-tune for a variety of different tasks, and also potentially for different languages, right? But one of the big benefits of this is, and which is quite surprising, is that by learning these kind of common representations, we are able to transfer knowledge and supervision from high web resource languages like, say, English, towards building models for lower web resource languages, say, which is pretty much all Indian languages, right? So in this attempt towards how we can transfer knowledge and supervision, this looks like a very, very promising approach to kind of learn these kind of common multilingual models, and then fine-tune them for a variety of different tasks for different languages. So with this in mind, so there have been a couple of pre-trained models that have been multilingual pre-trained models that have been proposed already. So MBERT, or multilingual BERT, was one model which was previously released by Google, along with kind of release of BERT in 2018-2019 timeframe. And MBERT actually supports 104 languages, including 11 Indian languages. But what happens is that now, since with a limited model capacity, since you are trying to cater to all of these 100+ languages, your performance kind of reduces, because you're not able to pay as much attention to all of these language-specific nuances that you would ideally want to do, right? So in order to, since we are interested in specifically doing better for Indian languages, so one question we wanted to ask was what will happen if we could just build a MBERT style model focused on Indian languages. And that's how Mural came about. Mural stands for Multilingual Representations for Indian Languages. So it's a BERT-based model for Indian languages, having around 236 million parameters, trained over 16 billion tokens. So it has the largest coverage as far as we know in terms of Indian language coverage. So currently covers 17 Indian languages, including English. And it supports both native scripts, like say Gurumukhi, Devanagari, but then also transliterated versions of those texts. So like, say writing all of these different language data in say Latin or like in Roman alphabets. So how well do we do? So we compared Mural against Embird, and we find that like on a variety of different benchmark tasks, we are able to do better, and on average with about 10 percentage point absolute increase in performance. Now this is about when you're working with native scripts, right? So where the inputs are in like Indian language inputs, but since the model also supports transliteration, so we also did the evaluations when all of the evaluation data is transliterated. And since Embird didn't have exposure to transliterated data, so we find that Mural's gains are even more higher in that particular case, where for transliterated data, we get about 27% absolute increase in performance. So, so the results that I'm showing you here is from the Mural base model, and which has this 236 million parameters. And more recently, we have also released the Mural large model, which has 550 million parameters, which is comparable to the, in terms of size, to the XLMR model, which is considered the current state of the art. And we are able to find that the Mural large model is either comparable or better than the XLMR model for a variety of tasks. And all of these, both Mural base and Mural model, are publicly available that you can try out if you are interested. So this is one example of trying to do transfer of supervision from high web resource to lower web resource languages. Oh, by the way, one point is that all of these experiments that I'm reporting here, those are all done in a zero-shot setting. That means the training is happening only for English, and the evaluations are happening on all of these different Indian languages for which we have evaluation data, right? So what's very interesting is that, say, if you take like this named entity recognition, here I'm probably evaluating this on like some 6 or 7 Indian languages, but the model has not seen training data from any one of those Indian languages. So it's trained purely on English data, and we are able to do zero-shot transfer, and with pretty respectable performance, I would say here, which is kind of increasing from some say 60% to close to 80%. So that's again kind of demonstrates the promise that these kind of multilingual models have in our ability to do this kind of knowledge transfer, knowledge and supervision transfer from higher resource languages to lower resource languages. Now, so that's great, right? So we are building this kind of language family specific model from Embird, right? But it results in kind of this kind of a forking behavior, where for different language families, I may end up and fork and train like a separate model, right? So we did Mural in our case with it's true that that results in improvement in performance. Similarly, there is say Arabic bird, there is Chinese bird, right? So now if you're creating all of these gardened model, then the whole promise of multilinguality is lost again, right? Because now you are kind of creating these hard partitions across languages. So we cannot exploit multilinguality. And then also in say, if you're running some production services, now instead of one model, now you have to say manage 10 different models, right? So that again increases the overhead in how you can manage all of these different models, and also not able to exploit the multilinguality. So in this merge distill work, we asked the question that whether we can merge all of these different language-specific models that have been trained and then merge them all back into one model without compromising on quality, right? So, and that's what here is the paper, which was presented in Findings of ACL this year. So that's again the idea, right? So the forking has been done. Previously, I talked about Mural. Other models are also there with similar type of forking in a language family specific manner. Now, whether we can do some sort of like, merging to get like a merge model, but also while retaining all of the goodness in performance, right? So that's what merge distill does. So it trains one student model from multiple teacher models, and the teachers can be a mix of multilingual or monolingual models in themselves, right? So one thing to keep in mind here is that there's lots of work on distillation, but all of that most of the distillation work happens in the fine-tune stage, right? So you have kind of like one task, like say NER, and then you are merging multiple NER models into say one. But in case of merge distill, we are doing this distillation during the pre-training stage. So this is a pre-trained distillation step as opposed to more standard fine-tuned distillation. So this is kind of pictorially demonstrating what's going on. So if you have language data from different languages, so you apply the respective teacher models that's kind of performing well. And then basically these teacher models provide you the annotated data on which the student language model is trained, right? And the student model basically combines and merges all of these different teacher models into one single model. So we do some evaluations, and what we find is that this merge distill student model is able to effectively combine all of these multiple teacher models into one single model without degrading in performance, and in certain cases also improving in performance, right? So please note that here performance improvement itself was not the goal. So the basic goal was whether we can combine all of these teacher models without degrading in performance. So we have achieved that goal, and in some cases also surpassed and did improvements on top of the teacher models. So so if you have this kind of like a setting where you have multiple language models floating around, and you think that it might be better to combine all of them into one model, so merge distill could be one effective way to do that. Now moving on to the second part, which is how we can leverage the relatedness among the Indian languages. So here we are interested in how we can adapt these kind of language models, like say Mural or Embird, towards other low web resource languages. And this is joint work with Sunita and her group at IIT Bombay. And I believe she will be talking more about it later today. So I'm just going to give you a very high-level overview of this work. And this was published in ACL 2021. So in the first part, we talked about the pre-trained language models, and we said that even if we have unlabeled corpora, we are able to make these significant advances, and as a community, I mean, and not just us. And in building these type of models and being able to do even zero-shot transfer of performance. But what you need in those cases is availability of some text corpora over which you can train this kind of pre-trained language model. But it turns out that for many Indian languages, even availability of unlabeled corpora itself is a challenge, let alone labeled data sets. So here is a plot of these 23 Indian languages, scheduled Indian languages, and a number of Wikipedia articles. So as you can see, English is way ahead with more than 6 million articles. Hindi has around, I think, 160,000. But towards the tail of these languages, for example, say Punjabi or Oriya, you only have hardly a few tens of thousands or a few thousands of documents, right? So the question is, how do we adapt these kind of multilingual models and incorporate a new low web resource language for which we may not even have large corpora to begin with, quickly into that pre-trained language model, right? So for this, we kind of try to exploit this relatedness among the languages. And we exploit relatedness from two angles. So one is the script normalization, which is done through transliteration. And the other one is that since these are all related languages, they have similar like in a sentence structure. So whether we can do some sort of cheap translation, which we call as like pseudo translation, to basically align data from multiple of these languages. So let's say we have Punjabi data, which is written in Gurumukhi script. And then we also have available with us, even though we don't have the large unlabeled corpora, but maybe building this kind of Punjabi Hindi bilingual dictionary is not that difficult. So we also have mappings of, like, say, Punjabi word in Gurumukhi to Hindi words written in Devanagari. And then given a Punjabi sentence, we first do transliteration, so which is kind of like, you know, converting all of these Gurumukhi script inputs to Devanagari inputs, right? So even though I was not able to read the Punjabi sentence, now since I can read Hindi, I can say, like, you know, yeah, ek bandar hai, right? So this is the first step of doing kind of like, you know, converting all of this script language data to the common script of Devanagari. And the second part is doing pseudo translation, right? So by doing just these single word translations, by leveraging some bilingual lexicon, now we are able to replace this bandar into, say, bandar or banar, which are these appropriate words in Hindi. And that way we get some sort of, like, you know, pseudo translated Hindi output, right? So you can think of it as, like, you know, by leveraging this kind of like transliteration, because the words are roughly similar, but they are written using different scripts. So we normalize all of them using transliteration. And since the sentences also have similar structure, so by doing some sort of local translation at the word level, we are able to kind of like map everything into some form of Hindi Devanagari. I mean, again, it's going to have noise. This is not a perfect process, but maybe the signal is higher than the noise, and then we basically put all of this data for pre-training. So I'm not talking about those details. So what we find is that, so we call this model, by the way, RelateLM, because it's exploiting this relatedness among the languages, which allows us to do this kind of transliteration and the pseudo translation without incurring too much noise. And what we are able to find is that compared to previous approaches, which kind of like tries to do this kind of some form of relatedness among languages, or tries to adapt to new languages quickly without exploiting relatedness, like say eBERT method. So RelateLM is able to do much better. So in this case, we are treating Gujarati as a low web resource language. So what's interesting is that compared to eBERT, which is trained on about like 80K corpus, RelateLM is able to do better, even with 1/4 that data, right? And when I say data here, this is just unlabeled corpus. I'm not talking about label instances here, right? So this is encouraging and kind of suggests one way using which we can adapt these kind of pre-trained language models quickly towards new low web resource languages, leveraging the relatedness that exists among those languages. So now moving on to the third part of how we can connect these kind of Indian language text data with knowledge graphs. And knowledge graphs are very important, and those are increasingly used in a lot of NLP applications. And in knowledge graphs, you can think of as basically large multi-relational graphs with entities and relationships among them. So we want to address this situation where I have say text in say Hindi or one of the Indian languages, and my knowledge graph is primarily present with labels which are in English, right? So the question is these kind of English facts, how I can link with non-English, or in this particular case, Indian language textual data. So basically the goal of this multilingual fact linking, or MFL in short, is how I can link KG facts to text in a cross-lingual way. So this is not a made-up problem. If you look at Wikidata, which is a publicly available knowledge graph, we find that the labels, names for these entities and relations in a variety of Indian languages is significantly poor compared to the names and the aliases that are present in these other languages. So definitely English, but also German, Spanish, right? So if you want to connect Indian language data, this becomes a very important problem to be able to bridge this gap. So with this in mind, we propose a model called RefCog, which basically has two parts. So one is the retrieval part, where given the text using a dual encoder model, we retrieve in a quick manner what are kind of likely relevant facts that are present in this particular sentence. And then with those top K retrieved facts, again, these facts could be in or are going to be in other languages and not necessarily in, say, Hindi or any of the Indian languages we care about. Then we have a constrained decoder, which basically is a sequence-to-sequence model, which finally outputs the fact which is actually present in this particular sentence. So you can think of this as like a retrieval plus generation mechanism for doing this kind of fact linking in a cross-lingual way. So in order to do this, turns out that even though this is a very important problem, but no data set existed. So we basically went ahead and created a new data set for this particular problem, which we call as IndicLink. So it's a first of its kind and covers 6 Indian languages and English, so total 7 languages. And even though we have prepared this for fact linking, so if you're interested in problems of entity linking or relation classification, this same data set should be useful for that as well. And since this is a new task, we didn't have prior baselines to directly compare against. So what we compare is basically our dual encoder retrieval only model or the generation only model, basically like the two parts that I showed, and then the RefCog model, which combines both of them together. So we are able to show that this composite model, which leverages both retrieval and generation, is able to do better, right? By the way, this setup of doing retrieval plus generation is also a generic idea. So usually people do kind of like retrieval followed by classification. But in that pipeline system, if you have made some error during the retrieval stage, recovery from that in the subsequent candidate selection or classification becomes difficult. But generation models have a possibility of recovering from that, right? So I think that's a general lesson here. Which could be applicable beyond this kind of fact linking problem. So both some methodological contributions and also a new data set which we prepared as part of this work. So in summary, today I talked about this multilingual representation learning or multilingual modeling, which gives us a great opportunity to kind of break this language resource barrier and help transfer resources and knowledge across languages. I talked about a few methods, merge distill, neural, merge distill, relate-LM, multilingual fact linking along these dimensions of transfer of supervision, a better model maintenance, how we can relate languages, and then how we can connect text data with knowledge graphs. And we have also talked about some model and data contributions in the form of neural and IndicLink. So we cannot do all of these things alone. So we have also created a new challenge called CHAI, which stands for Challenge in AI for India. So this is a question answering challenge, which is live on Kaggle for 2 Indian languages, namely Hindi and Tamil. And there are more than 700 plus teams that are already participating with great advances over the last 2 months or so. So this is going to run until mid-November. So if you are interested in making method data contributions, I think this is a great platform. So I definitely encourage you to take part in it. So in closure, I'm very passionate about this area of how we can make advances in Indian language processing. And when I say language, I mean both text and speech, which is also super important in the Indian context. And this provides an excellent area for doing foundational research and then also have deep societal impact. So if you are looking for PhD thesis or thesis topics or BTech problem topics, I think it's a very, very fertile area with lots of exciting work to be done. So I encourage you to take a close look in this area. So I'll finish here, and thanks for your time. And if you're interested in learning more what we are doing at Google in these areas, I encourage you to visit this URL. So thanks again for your time, and I'll be happy to take any questions time permit. Thank you.
Thank you, Dr. Talukdar. So there are a lot of questions that have come up. I'll start with the first question, which is, when you're trying to combine languages that do not have any common traits, let's say from two different language families, in that case, wouldn't it be better to use the same language families and group them together in the merge models that you were trying, the student-teacher models also, rather than bringing in Arabic and Mural together?
Yes, yeah. So I mean, one thing is that there are kind of some evidence that if you bring these kind of somewhat disparate languages also, there is positive transfer that's happening, right? Although our understanding of what it's really learning and how it's able to learn these kind of alignments across languages is still very much in infancy. So there are some hypotheses. So I think there is some evidence that even if you combine these kind of unrelated languages, there is some benefit to be had, right? But it is possibly true that if you kind of combine these kind of related languages, you might be able to do better transfer. So we are kind of taking both of these approaches. So maybe kind of you do first a language family specific model, so where you are able to do better transfer, and then maybe combine that across families to kind of still have the benefits of multilinguality flow across language family barriers.
Right, thank you. So another question. So this relate LM pre-trained model that you have, whether it will be made public and whether we can use it for fine-tuning later.
I think it's already made public, yeah. And if not, please let us know. And I think, yeah, this is all open work. So, but definitely the code is there, and maybe the pre-trained model itself should also be available.
Thank you, Dr. Talukdar. Thank you very much. Over to you, Amit.
Thank you so much, Sarit, for moderating the Q&A. And of course, I'd like to thank Professor on behalf of everybody here on the summit. Thank you so much for such an innovative and an extremely, extremely interactive and engaging segment. Thank you so much once again, Professor.